Okey doke.
I don't have any specific questions. I am kind of having a slight issue with balancing out the equations.
Okay, well, let's get to work then.
All right,
I have some problems from the back of the book, and we'll take a look at those, okay?
perfect.
Okay. So, can you see what I have written here?
I can, but it's blurry.
Not on my computer. Are you sure?
I am pretty sure. I can exit and try to log back in. It's pretty blurry on my side.
Okay, I'm messing with
You're clear, but oh, okay. There we go. Oh,
I'm trying to get you to
it was clear a minute
your
ago.
sanity.
Ah, yeah, I'm not quite sure I have much sanity left with all of my children.
Well, let's take a look here and see what we can do, okay?
All right.
So write an equation. We'll move this a little bit. From the following description. So the reactants are gaseous NH3 and O2. Reactants means that they are going to combine together, or that's what you start with. So we're going to write NH3, and below or above it says gaseous, so we use a G for that. And then O2. And since they don't tell us a different state for O2, we're going to assume gaseous. And when you have things react together, the normal thing to do is put an arrow. And that means they become, or they produce, or they make. And we have gaseous NO2. So again, we're going to put the state in parentheses behind the formula of the compound. And liquid H2O, and for liquid, we use an L. So this is the reaction written out, but it also says stoichiometric coefficients of 4, 7, 4, and 6 respectively. And the respectively means that these coefficients fit the formulas as they were given in the same order. That's all. So this is the equation that you would write out. And the important thing to remember from this equation are two things. We could say 4NH3 are equal to 7O2 are equal to 4NO2 are equal to 6H2O. And we could even put words here. We could say 4 molecules equals 7 molecules equals 4 molecules and equals 6 molecules. So this means if you start with 4 molecules of NH4 and you have more than enough oxygen to react with this, you will make 4 molecules of NO2. So do you understand the equality here?
Yeah.
So if we start with 4, we should end up with 4 of these. If we start with 4 of these, we should end up with 6 of these. If we start with 7 of these and react them all, we should end up with 6 of these. Or you could say, if I want to make 4 of these, I need 4 of those to begin with. Another way to think about this, though, and it's more important for us, is 4 mole of NH3 is equal to 7 mole of O2 is equal to 4 mole of NO2 is equal to 6 mole of H2O. So these coefficients mean both things. So for instance, if we start off with 1.00 times 10 to the 23 NH3, and we want to calculate how many H2O we're going to make, how do we do this? Well, we would say you get 6 H2O for every 4 NH3, and then we would have our answer. And the answer would end up being, let's see, 1.5, it would end up being 1.5 times 10 to the 23. 1.50. So you see how we used this to calculate that?
Yeah.
Now, what if we had instead 5.1 mole of NH3, and I wanted to know how many mole of H2O we were going to make? What would we multiply by here? And here, since we have moles, we would use this bottom line, and I would say 6 mole of H2O per 4 mole of NH3. And we would end up with an answer of a 7.6 or 7.7. Let me actually get the correct number, zig figs. It's going to be 2. $7.7. Now, do you notice in both of these, I use labels, because if I wrote this, and you didn't know what you were looking at, you would be asking, well, moles of what?
Right.
So this is a bad way to do it. You want labels. So this is a perfect way to write out the answer to those questions about how many H2O molecules and how many moles of H2O. Any questions about that?
No.
And that all comes from balancing the reaction.
Okay.
And here you've learned a new term now, stoichiometric coefficient. That's what that is. These are all stoichiometric coefficients, but normally people say coefficient.
Okay.
Okay. Here we're using stoichiometry with the coefficients. Here they're just coefficients. Now, since you're the only one here, I just want you to give me a verbal, I'm ready to go, and we'll do the next problem.
Go for it.
Okay, I shall. So in this problem, we have the equation for the reaction of aluminum and bromine is 2 aluminum plus 3 bromine gives you Al2Br6. If you could use 6 times 10 to the 23 molecules of Br2, how many atoms of Al will be consumed? So we're going to start with 6.0 times 10 to the 23 molecules. And here I'm not going to write molecules of Br2, I'm just going to write Br2s. Now, what are we going to multiply to get aluminum atoms? Well, we're going to look at our equation. You see that we have 2 aluminum atoms here?
Yeah.
So I'm going to write that, 2 aluminum, and we have 3 bromines here. And we'll get our answer. 3
Okay.
goes in. 3 goes into 6 2 times. 2 times 2 is 4, so it's going to be 4.0 times 10 to the 23. And if you wanted to, it'd be okay to do things like this. Molecules of Br2 times 2 aluminum atoms per 3 molecules of Br2, and your answer would be 4.0 times 10 to the 23 atoms, well, aluminum atoms. Okay. So you can write that out too, so that you end up with aluminum atoms. Now, why do they call it a molecule of Br2, but they call it an atom of aluminum when they're both pure substances? And the answer is pretty simple. There are 7 elements that come in pairs where the atoms are bonded together. Whenever 2 atoms bond together like that, it's called a covalent bond.
Right.
And that's called a molecule.
Oh, okay.
So what is the smallest unit of an ionic compound? The ions. What's the smallest unit of a molecular compound? The molecule.
Right.
So single atoms are not considered to be molecular compounds. But
Right.
when you have two nonmetals, that's a molecular compound. Do you remember the 7 nonmetals that make diatomic molecules? Okay, I'm just going to say it. Hunkelbrief.
Yeah, I didn't remember that.
On, coal, brief. So what does H stand for?
Hydrogen.
O.
Oxygen.
Yep. N.
Nitrogen.
Cl.
Chlorine.
Yep. Br.
Bromine.
Yes. I.
Iodine.
And F.
Fluorine.
There you go. So those are the 7 elements that make diatomic molecules when you buy a jar of it.
Okay.
Questions about this one?
No.
Okay, so we'll put that off to the side. And next we have a 0.2 gram sample of magnesium burns in air to form 0.2 mole of solid MgO. What amount moles of oxygen is required for the complete reaction? So when this says that this sample burns in air, you know that magnesium is going to be one of your starting materials. And it's not a Hunkelbrief, so you don't say Mg2. It is a metal, and we know metals are solids at room temperature except for one metal, which is mercury.
Right.
So that's what we start with. And I'm going to put an arrow here, and it says it makes solid MgO. So, and it burns in air. So does this have to react with anything to make MgO? And the answer is yes. There's oxygen over here on the right, and there's no oxygen on the left. There has to be a source of oxygen, and it probably comes from the air.
Right.
So what is the most likely thing coming from the air to react with magnesium to make this product?
Oxygen.
Good. Oxygen is a Hunkelbrief. So what do we write? We write O2, and it's a gas. Now, what are the sources of oxygen are in the air? Well, a very common source, not too common, but it is in the air, is carbon dioxide. Could we write carbon dioxide here and be as happy with that as with O2?
No.
Why not? You're right, but why not?
Because there's no carbon in the product.
Correct. So that's why we wouldn't want to say CO2. There's no carbon over here.
Okay.
So that's why O2 makes the most sense. Okay, good. Okay, so here, let's balance the reaction. Now, to balance the reaction, there's one do and there's one don't. Do, change coefficients. Now remember, the coefficient is the number in front of the formula telling you how many of that you have, how many of that formula you have. Don't change formulas. That's all there is. One do, one don't. So let's do a don't for the above. I'm going to rewrite this, and then I'm going to show you the don't. So do you see that we have one magnesium here and one magnesium there?
Yeah.
That's balanced. Do you see that we have 2 oxygens here and 1 oxygen there?
Right.
That's not balanced. So I'm going to put a 2 there, so that way we now have 2 oxygens on the right. What did I do to this formula?
You changed the formula.
You're not allowed to do that. So this is a don't. Whoop. So I'm going to rewrite this below. And you'll notice when I'm rewriting it, I always leave a little bit of space to put coefficients here.
Right.
So the idea is to make sure that the number of magnesium atoms on the left of the arrow equals the number of magnesium atoms on the right of the arrow. And we've got 1 and 1. And then we do the same thing for oxygen. We've got 2 and 1. So what can we do to make this even up? And I'm going to say, well, I'm going to put a 2 there. And now I have 2 oxygens and 2 oxygens, correct?
Yes.
But I also know that that now changes my number of magnesium, so I have to revisit magnesium. So I now have 2 magnesiums here and I only have 1 over there. What can I do?
Put a 2 in front of it.
And there you go.
Okay.
Now it is balanced. You have 2 magnesiums on the left, 2 on the right, 2 oxygens on the left and 2 on the right.
Okay.
Now, you might say, well, but the magnesiums were good beforehand. And when I did this, I messed up the magnesiums. Sometimes you have to, what's the saying? You have to break a few eggs to make an omelet. I think that's the saying. So sometimes you will mess up some other coefficient and have to adjust.
Okay.
Now, here's a little trick that some people like. One magnesium, right?
Right.
2 oxygens, 1 oxygen.
Right.
If I put a 1/2 there, how many oxygens do I have now?
1.
1. But we don't like ratios like this. So what do? We double everything. So what happens when we double 1?
It becomes 2.
What happens when we double a half?
It becomes 1.
And what happens when we double 1?
It becomes 2.
So this is a kind of useful trick. It's the half trick, if you will.
Okay.
Go ahead and use a half coefficient, but then double everything. Okay?
Perfect.
Ready to move on?
Yeah.
Don't let me rush you. I see it looks like you're still writing stuff down. So when I ask you, are you ready to move on? It's okay to say, I'm still writing some things down.
Usually when I'm still writing and I say I'm done, I have 1 word left.
Okay. I just don't want you to feel rushed.
Oh, no.
Okay. Now, number 8, write balanced reactions for the following. So let's take a look at A. Production of ammonia. Does that make ammonia seem like it's a reactant or a product?
A product.
Right. And so that means we're going to put it on the right-hand side of the arrow. Because in these chemical reactions, the products are what the arrow points to. The reactants is where you start. They really should have called them, instead of reactants and products, they should have called it starting things and ending things.
Right.
Right?
The start and the end.
Or instead of reactants, maybe you could have made it like a ingredients and product.
True.
Okay. So we're going to combine N2 and H2. So what would you like to change first? I'm going to tell you my preference. I usually start at the right and work towards or start at the left and work towards the right.
Okay.
So I'd start with nitrogen.
And there's 2 on the left and only 1 on the right.
So what do you want to do?
So you would have to put a 2 on the right.
Okay. So here we want to get used to the terms. You want to say, put a coefficient of 2 on NH3.
Right.
Okay, great. How do the hydrogens look?
Not balanced.
So what do you want to do? How many here?
There's 2 there.
How many here?
6?
Now, let's take a look at this. Yes, there are 6.
Okay.
Because the 2 really means 2 of them, right?
Right.
So 3 plus 3 is 6. Another way to do 3 plus 3 is 3 times 2. So if you
Right.
take the coefficient and multiply by the subscript, that tells you how many.
So you want to put a 3 on the H2?
And you're done.
Okay. Perfect.
Now, this is spelled incorrectly. It should be methanol. So we have H2 gas plus CO gas gives you CH3OH liquid. So what do you want to do first?
Start with the H2.
Okay, how many here on the left of the arrow?
2.
How many on the right of the arrow?
3?
No.
No. Oh, wait. I'm confused.
Aren't there
4.
There's 4,
4.
not 3. So you got it. This one is trying to teach you a lesson that sometimes the
My
formula,
brain was trying to multiply 3 times 1 instead of adding.
there's 3 there and 1 there. There's no coefficient, so there's no multiplying. Okay, so what do you want to do to make this work out?
Multiply by 2.
So coefficient of 2 over here. Now, how many carbons on the left?
1.
How many on the right?
1.
Good. How many oxygens on the left?
1.
And how many on the right?
1.
We're done.
Okay.
Okay, production of sulfuric acid by combining sulfur, oxygen, and water. So for sulfuric acid, we start off with this formula, SO4 2-, that's the sulfate ion. To get the acid, you add 2 hydrogens to it and make it neutral. I know it's 2 hydrogens because of the -2 charge. If it were -3, I'd add 3 hydrogens. If it were -1, I'd add 1. So that's sulfuric acid. And that's what we're going to make, H2SO4. We're going to make it from sulfur, oxygen, and water. So what do you think of what we have so far? Does that look okay?
Yes, except for you forgot to put what's gas and what's liquid.
We're not going to worry about that because they don't really talk about that.
Okay.
But also, are there any Honkelbriefs here?
Oxygen.
Yes.
And hydrogen.
But well, there's no hydrogens in here that are by themselves. Remember, the Honkelbriefs are for the pure element. So that's pure oxygen. Okay, so what do you want to do first?
Balance out the oxygen because the sulfur is already balanced.
The oxygen's going to be difficult because you have 2 here, 1 here, and 4 there. How do you want to go about doing that?
Oh,
Maybe we should skip it and we should go to hydrogen.
okay.
You know, when an element is spread out amongst so many of the things in the formula, it's kind of hard to do.
I see that.
So let's go for hydrogen. We have 2 here and 2 here. So we're done with hydrogen. Now we are forced to deal with oxygen.
Okay.
How many oxygens on this side?
4.
4 oxygens. How many on this side?
3.
3 oxygens. So here's a question I have for you. If we change the number in front of the H2O, that changes the number of hydrogens, and then that changes this. And then when I change this, I have to go back and do sulfur, and we have to monkey around a lot, right?
Right.
So we can try that, or we can ask ourselves, is there a number I can put in front of this so that I will end up with enough oxygens to add to that one and get 4 oxygens? Do you understand the question?
Yes
I
and
let-
no.
If I let that be X,
Oh, okay. Well, leave my door open then. Leave it open. Close the gate so I can watch him.
if I let that be X, because we don't know what it is, but I want to keep this as a 1, couldn't we say that X times 2 plus 1 times 1 has to equal 4?
Right.
Okay, if that's the case, what is X equal to?
2.
No, you're going too fast. You're doing it in your head. Isn't this the same as 2X?
Yes.
And what's 1 times 1?
1.
Okay, now if I take the 1 onto the other side, what does this become?
2x equals 3.
And then what is X equal to?
3 halves.
3 halves. So if I cross out this and I write S plus 3 halves O2 plus H2O gives you H2SO4, what do I need to do to get rid of the 3 halves, but keep the ratios the same?
Double everything?
Double everything. So I'm going to call this 2. And 3 halves doubled is just 3, right?
Right.
And what is 1 doubled? That's a 2, and this is a 2. And let's check and see if it works out. So I'm going to write S O H. So how many S's on the left?
2.
How many oxygens on the left?
6. Sorry, 3.
No.
No? Oh, wait.
3 times 2 is 6. What about these two?
Oh.
6 of them here. How many are here with the 2 H2Os?
8.
8 total. That's correct. How many hydrogens?
2.
4.
4.
2 times 2. Okay.
Okay.
So you can take the coefficient, multiply by the subscript to get how many? 2 times 2, 4. 3 times 2, 6. 2 times 1, 2. 6 plus 2, 8. 2 times 1, 2. So hydrogen, sulfur, oxygen. How many hydrogens?
4.
How many sulfurs?
2.
How many oxygens?
8.
So do they match?
Yeah.
They do, but it's kind of hard to tell, isn't it?
A little bit.
Do we have to,
Tired doesn't help with the math.
do we have to make the list the order in which we find the elements? And the answer is no. If it were me, I'd make the list the same way I did on this side. And I'd find 2 sulfurs, 8 oxygens, and 4 hydrogens. And when I compare these two lists, it's very easy to see they are the same.
Okay.
Now, we could do this one by brute force. So here's the brute force method. Okay, so the brute force says, okay, that's 2, that's 2, that's 1, that's 1. That's 4 or 2, and that's 1. So you start off with something like this. I'm going to put a 2 there. Why a 2 there? Because I got 2 oxygens there and 1 there, 2 there for 4, which matches the 4 over there. Okay?
Okay.
Now this is the break a few eggs to make an omelet time. When I put the 2 there, I mess up the number of hydrogens, don't I?
Yeah.
So how do I fix that?
You added 2 to the other side.
Okay, so now I have my 4 hydrogens and the 4 hydrogens, but now I've messed up sulfur. I'm going to leave that for later. Now, how many oxygens do I have on the right now?
8.
How many over here on the left?
4.
Now, I need 4 more oxygens. I can either change the number in front of O2 or change the number in front of H2O, or I can do a combination of both. The wisest thing to do is to change the number in front of O2. Because if we change that, we're not changing sulfur or hydrogen, so that we don't need to worry about those impacts. If I change the number in front of H2O to get more O2s, then I have to go back and say, well, what happens to hydrogen? So what number can I put in front of O2 to get 8 H2Os?
4.
Excuse me, to get 8 oxygens.
4.
Well, remember, there's 8 oxygens total over here, right?
Right.
I want 8 total over here. How many do I have now?
Oh, 10.
So that's no good. 4 is too many.
3.
Let's try that. How many oxygens now?
8.
So we're good on hydrogen and we're good on oxygens, aren't we?
Yes.
Now let's deal with sulfur. How many sulfurs over here on the right?
2.
How many do we need on the left?
2.
Now, when I change this, does this change the number of hydrogens or oxygens?
No.
No, it does not. So I don't need to worry about those getting upset, right?
Right.
So this is the brute force method. And you can see that this answer ends up being the same as the answer we had before.
Okay.
We didn't have to do any doubling.
Right.
My point here is simply that there's more than one way to balance a reaction.
Okay.
Okay. So let's look at balancing these following reactions. So for A, what do you want to do first?
Well, the CRs are balanced, so look at the CLs.
That's correct. Now we have 2 here and 3 here. What are you going to do about that? Because if I double that, I get 4 and it still doesn't work. If I double that, I get 6 and it doesn't work. It goes back and forth. But let me ask you this. I've got 2 here and 3 here. Do 2 and 3 are 2 and 3 factors of some number?
6.
6. So what if I shot for 6 chlorines on the left and 6 on the right? What would I put in front of Cl2?
A 3.
Okay. And what would I put in front of CrCl3?
A 2.
Okay, so what we did is we found the smallest number that they both factor into, and we decided I want that many chlorines. Capiche?
Yeah.
Okay, now it's really simple because if you look at the chromiums, all I have to do is ask how many chromiums on the right.
There's 1 on the right and 2 on the left, so you would add a 2. Or sorry, my lefts and rights are backwards. There's 1 on the left and 2 on the right, so you want to make the 1 on the left a 2.
And you're done.
Okay.
The only thing this needs to be better are the states that we're given with the problem. Okay, how about B? Do the silicons match?
Yes.
Do the oxygens match?
No.
So what do you want to do about that?
Put a 2 in front of the CO on the
Right. Okay.
Today is not my day for directions.
On your table, I want you to paste 2 little cards, one that says left. Okay. So now the carbons are off. What do you want to do about the carbons?
Add a 2 on the left.
I fell off a scooter.
And you're done.
Okay.
I fell off a scooter and then somehow my
Give me just a second.
Sure. Okay, let's take a look at this last one. You got 1 iron here and 3 over here. What do you want to do?
Put a 3 on the left.
You got 2 hydrogens here and you got 2 over here. What do you want to do?
Leave that one alone.
Okay, and we've got 1 oxygen here, but 4 over here. What do you want to do?
Put a 2 in front of the H2O.
Okay, how many oxygens do you have on the left now?
You have 2.
How many do you have on the right?
4. That is still wrong.
I think what happened is you looked at this 2 and you thought maybe that belonged to the oxygen, and it does not.
No. So a 4.
Okay, that I think sounds better. And how many, now you'll notice this changes the number of hydrogens. So that means we need to revisit hydrogen.
Right.
How many hydrogens on the left?
8.
And how many on the right?
2.
So how do you want to adjust that?
Multiply the hydrogens by 4.
Okay. And you can always make a little list and check it out. 3 irons, 8 hydrogens, and 4 oxygens. 3 irons, 8 hydrogens, and 4 oxygens. 384, 384, boom, we're done.
Perfect.
So the deal is on an exam, you have no excuse for coming up with an unbalanced reaction if you know how to count atoms.
Right.
Okay. For the following equations, name each reactant and product and balance them. So what about A? Let's balance first and then we'll name them.
Okay.
How many sulfurs?
1 and 1.
Okay. How many fluorines?
4 and 1.
So what do you want to do?
Multiply the right by 4.
Like that?
Yeah.
Okay. So normally when I balance things, I just work from left to right. And I don't try to do the whole thing at once. I just do it element by element, normally. How many hydrogens on the left?
4. Oh, wait. 2.
How many on the right?
4.
So how about a 2 here?
Perfect.
How many oxygens on the left?
2.
How many on the right?
2.
So it looks like we're done. Now let's name these. This would be sulfur. What's the prefix for 4? Tetra.
Tetra. For some reason, I was thinking quad, which does not work.
Quad works for vehicles.
Right.
What's the name of this guy? Dihydrogen monoxide. So these are molecular compounds with 2 parts to the name.
Okay.
What would this one here be called? It'd be called sulfur dioxide. And this one would be hydrogen monofluoride. Now this one has a common name. It's called hydrofluoric acid,
Okay.
which sounds like hydrochloric acid, which is similar to this, only it's HCl. Okay, that's A. Are you good?
I'm good with A.
All right, let's go to B.
Okay.
Okay. How many nitrogens on each side?
1.
How many hydrogens on each side?
3 on the left and 2 on the right.
Oh, we ran into this before. This sounds like a 2-3 type of thing, doesn't it?
Yes.
Like we're going to put a 2 here and a 3 there so that we get 6.
Right.
Okay. Oh, now we got to go back and do nitrogens.
So 2 in front of NO on the right.
Okay. How many oxygens?
Now
On the left.
2.
On the right.
2. Wait. 3.
5.
5.
2 there and
And
3
3
there
there.
for 5.
Whoa.
Right? 3 and 2 for 5, right?
Right.
But they come in pairs. So what are we going to do?
And then double everything.
Okay. And since we're really unsure about the doubling thing, we're going to check. How many nitrogens on the left of the arrow? This way.
4.
4. How many hydrogens on the left?
12.
4 times 3, 12. How many oxygens on the left?
10.
Okay, let's look on the other side, the product side. How many nitrogens in the product side?
4.
How many hydrogens in the product side?
12.
How many oxygens in the first product?
4.
How many oxygens in the second product?
6.
And 4 and 6 are?
10.
Do we have a match?
Yes.
We're good. Let's name these. What do you call this one? Nitrogen trihydride. It's also called ammonia, and you should know that name.
Okay.
That's 2 M's there. Ammonia. What do you call this guy? You call it oxygen.
Oxygen.
What do you call this guy? Nitrogen. And you have to use a prefix for the second element, monoxide.
Okay.
And how about this one? Dihydrogen monoxide. We could call it water. Why can I call this water? Because of this L. When H2O is a liquid, its common name is water.
Okay.
If this said H2OG, we couldn't call it water. What do you call H2O when it's a gas? Steam.
Steam.
And if this said H2OS, what would it be?
Ice.
Right. So we could call this water because it has an L there. Okay, let's try letter C. This time, let's name these things first. What do you call this guy? What's B stand for?
Bromine.
Boron.
Boron. Wrong one.
Okay, boron. And what do you call that last part?
Trifluoride.
That's right.
Okay.
How about this next one?
Water.
Let's give it the name that we learned for using those rules we learned.
Hydrogen monoxide.
Dihydrogen
Dihydrogen.
monoxide. So for the first element, you use a prefix if there's more than one. Second element, always use a prefix.
Okay.
Okay, how about the next one?
Hydrogen fluoride.
Monofluoride.
Monofluoride.
Always use a prefix on the second element. Now this one is hard to name unless you recognize that this is the borate ion. So this would be called bromic acid.
Okay.
But that one I wouldn't expect you to be able to name. Let's balance it.
So there's 4 hydrogens on the right. So put a 2 in front of the hydrogen on the left.
Okay.
And there are 3 oxygens on the right and only 1 on the left.
No, there's 2 on the left now.
Oh, 2 on the left now. I was looking at the wrong one. I always end up looking at the original instead of where I'm
Well,
working.
if you have trouble keeping track, just do this. So how many borons on the left, right? I'm going to get rid of all the coefficients. How many borons on the left?
1,
And on the left in the reactants, how many fluorines?
3,
How many hydrogens?
2,
How many oxygens?
1,
On the product side, how many borons?
1,
Fluorines,
1,
hydrogens,
4,
oxygens.
2.
Okay, so I usually start on the left. Borons are good. What do you want to do about fluorines?
Multiply the 1 on the right by 3.
Okay, so now I'm going to cross all of these out, all of them. How many borons?
1,
How many fluorines?
3.
There darn well better be, because we changed that number so that there should be 3, right?
Right.
Okay, how many hydrogens?
6,
6. How many oxygens?
2.
This is a 3.
Oh, 3.
And the reason you got that wrong is because I didn't have the 3 written out very well. Okay, great. Borons are on board, fluorines are on board, hydrogens are not. So what do you want to do?
Multiply the hydrogens on the left by 3.
Okay. So cross these all out. How many borons?
1,
How many fluorines?
3.
And those should not have changed because this number does not go in front of boron or fluorine. So that's good. How many hydrogens?
6.
And there better be 6 because that's how many we wanted.
Right.
How many oxygens?
3.
Oh, geez, we're done. The oxygens match.
Okay.
Okay.
That makes it a little easier.
If you make the list, it sometimes helps.
Okay.
And, I would say for beginners, make the list. It may take you a little bit more time, but it will help you to become faster later with confidence.
Right.
It's kind of like training wheels. Training wheels make you ride a bicycle better, faster, and eventually you don't need them.
Right.
Okay, for this next one, we have to talk about this idea of equilibrium, okay?
Okay.
So some reactions are reversible. Now, what that means, this is an example that is reversible. Hang on a second here.
Okay.
Calling from Cole Family Eye Care. I'm just checking in with you to see if whenever you have a chance when you're thinking.
So in this reaction, this is an acid, and acids make H plus in solution. So here, this is an acid that is making an H plus. This is the thing that becomes H plus right here.
For some reason, your share screen is frozen or paused. There we go.
Right. Sorry about that.
That's okay.
Hang on a second. I'm going to stop my recording because I'm going to get this beeping sound, which I hate.
Okay.
Okay, so this is a definition of an acid, something that makes H plus in water. Okay?
Okay.
And there are strong acids and weak acids. This is an example of a strong acid. And so if it's going to make H plus in water, here it is. Now, what remains if this guy gives up a hydrogen? And the answer is a chlorine. And then for this chlorine, we have to figure out what the charge is on this chlorine. Can you see over here that the charge is overall 0?
Right.
And this is +1. So what does this have to be to make the overall charge on the right 0?
-1.
Right. And do you see how that's the same way above? This is neutral, -1, +1. So this is an example of a strong acid. So if I put HCl into water, every HCl dissociates and makes an H plus and a Cl minus, every single one of them.
Okay.
A weak acid doesn't do that. A weak acid will also come apart. So here's an example of a weak acid, H3PO4. I put that into water, it makes H plus. Now, if it gives up 1 hydrogen, how many hydrogens are left out of the 3 we began with?
2.
Okay. And then there's PO4. What charge must this have so when we add these two together, they become neutral?
Can you repeat the question?
The
Sorry.
charges have to add up to 0. So what does the charge on this have to be?
Minus.
Good. Now, this is another example of a weak acid. So when this gives up an H plus, what's left over?
1 hydrogen.
1 hydrogen and a PO4. What's the charge on this have to be?
Minus.
Well, if it's a minus and that's a plus, that adds up to 0, and this has a -1 charge on it.
Oh. -2.
Correct. This is also an acid. So what does it make?
H plus
Good, good.
plus PO4 to the -3.
Correct.
Okay.
Okay, so these are all weak acids. Now, when I said that you put this in water, every one of them does this, every one of them. When you put this in water, 1 out of 100,000 does it.
Okay.
One out of 100,000. And when you put this into water, 1 out of a million does it. And when you put this in water, 1 out of 1 billion does it. These are considered to be weak acids because they don't come apart completely.
Okay.
Now, here's how we show this in chemistry. Do you see what I've done here?
Yeah.
So we use 2 arrows, one going one way and one going the other, because in this reaction, you have the forward reaction happening and you have the reverse reaction happening. So we call these equilibrium reactions. Where you have a forward reaction and a reverse reaction.
Okay.
Here, there's only a forward reaction, so that's not an equilibrium reaction.
Right.
Furthermore, with the equilibrium reaction, we say that the system or reaction is at equilibrium when the forward rate equals the reverse rate.
Okay.
Now, the amounts do not have to be the same. When the rates match. When I say the amounts of reactants and products. That is to say, at equilibrium, we won't have 50 of these, 50 of these, and 50 of these. That's not equilibrium.
Okay.
Equilibrium is when the change is the same. So imagine this, an equilibrium reaction between you and a millionaire, okay? Who's got more money, you or the millionaire? Well, for
Millionaire.
me, it's the millionaire because I don't have $1 million, okay? So imagine I meet a millionaire on the street and I give the millionaire $1 and they give me $1. Does their amount of money change?
No.
Does mine change?
No.
But yet the millionaire has more money than I do, right?
Right.
But that's equilibrium because the rate of change is the same.
Okay.
Now, when is the system not at equilibrium? Well, for me and the millionaire, if the millionaire was giving me $1 and I was giving the millionaire $2, which seems to be the case so many times, that's why the rich people get richer. So if I gave them $2 for every one they gave me back, that would not be equilibrium.
No.
And they would just be getting more and more money and I'd be getting less and less. And the reverse would also be true. If they were giving me $2 for every $1 I gave them, that would not be equilibrium either.
Right.
So equilibrium is when you have a reaction that can go forward or reverse. And when the forward rate equals the reverse rate, you have equilibrium. Furthermore, when you are at equilibrium, the amounts don't change even though the reaction's happening.
Okay.
Like the millionaire and I, if I'm giving him $1, he's giving me $1. There's stuff going on, but the amounts don't change. Fair enough?
Yeah.
So that's the idea of equilibrium. And then we have these things called equilibrium constants. And these are things that you want to understand but not memorize. We use the letter K for an equilibrium constant. So you have A plus B, and actually I'm going to make this A, B, B, D, D, and E, E. I don't use C, C because uppercase C and lowercase c look the same.
Right.
So K is basically the amount of products divided by the amount of reactants. So in this particular case, it would be K D raised to the little d power. So the coefficient becomes how many for the power?
Okay.
So we would have E raised to the little e power. And on the bottom, you have A times the little a power and B times the little b power. So this is the equilibrium constant. And the reason they call this equilibrium constant is because when this is at equilibrium, this number does not change.
Okay.
Okay, so I want you to take a look at this reaction here for a strong acid. Like HCl. So here, if you look at the products here and the reactant here, what are you going to have more of, product or reactant? One-way arrow.
Oh, the one-way arrow means the product is
Right. So
bigger.
K is going to be product over reactant. And if the number on top is big and the number on bottom is small, here's what we can say about K. It's going to be bigger than 1. Now for weak acids, like this one, K is going to be less than 1. Because remember how I told you, and if you don't remember this, it's no big deal. But in these equilibrium reactions, usually it's like 100,000 of these and 1 of each of these.
Right.
So if you can imagine in this equation here, you've got 1 times 1 over 100,000. Is that going to be less than 1?
Yeah.
A lot less than 1, right?
Oh, yeah.
So for weak acids, the equilibrium will be less than 1. And the way you use equilibrium constants, you say, well, if it's bigger than 1, it's product favored. If it's greater than 1, product favored. And if it's less than 1, it's reactant favored. And the deal is that strong acids are product favored and weak acids are reactant favored.
Okay.
Okay, so we probably have enough information to be able to answer the question. So all chemical reactions are product favored at equilibrium.
No.
No, weak acids are reactant favored at equilibrium.
Right.
So no. There is no observable change in a chemical system at equilibrium. So this is the one where the millionaire is giving me $1, I'm giving them $1. That's equilibrium.
Right.
Will you notice a change in how much money the millionaire has?
No.
How about the amount of money I have?
No.
So that's no observable change.
Stop.
So the answer for B is true. No observable change.
Okay.
Is the chemical reaction still happening? Yes, but we're not going to see a change in amounts. Okay, in equilibrium, evolving a weak acid in water is product favored. And here, what did we find out about weak acids? They're not product favored, they're reactant favored.
Right.
Okay. Well, we've gone for 1 hour and 15 minutes, so we should probably call it quits.
All right.
This morning, we did get a little bit farther. And so you may want to look at, I think we did 18, we did 20, 22, and 24 and 26. So you might want to look at the morning videos to see those.
Okay.
Okay.
Perfect.
Thanks for attending.
Thank you.
Appreciate it. Bye-bye.
Bye.